Hello everybody, this is Dr. Christopher White and welcome back for part 2 of our video series dealing with the lab exercise Paleozoic Orogenies of North America. So we're going to begin by looking at the Danville quadrangle map from Virginia. So the Danville quadrangle map consists of a sequence of late Proterozoic and Cambrian age metamorphic rocks that have been deformed by Paleozoic and early Mesozoic tectonism. So if we look at the Danville quadrangle map over here in the top right, straight away you'll begin to see that it looks pretty complex. However, there are some indications straight away of what may have happened to this area. So you've probably already picked out up here in the northwest, there is clearly some kind of feature that is closing up down here. This would strongly suggest the presence of a very large anticline or syncline straight away. We can also see that this region down here clearly shows quite complex deformation. If you look at these blue units in particular, you can see that they are definitely folded. And we can see the same thing over here in the east, where we have these dark pink and lighter pink units, which once again are showing strong indications of having been deformed. So straight away, we are beginning to get some idea that this area has probably undergone some kind of compressional deformation at some point, which would begin to suggest that it has been affected by an orogeny or orogenies. Now, in terms of the deformation itself that's affected this area, it has led to the formation of several large anticlines and synclines, which would be expected, and that would suggest compressive stresses. The area has also been intruded by Ordovician and Mississippian aged felsic intrusions. So straight away, the presence of these felsic intrusions is another indicator that some kind of orogenic process has taken place. Because if you remember in the previous video, we were discussing how these intrusions of intermediate rocks and felsic rocks, so tonalites and granites, are typically formed by the melting of continental crust associated with even subduction or crustal thickening produced by a continent-continent collision. So the presence of these felsic intrusions is another indicator that the area may well have undergone some kind of tectonism. Now, across the map area, we also have the addition of late Triassic to early Jurassic diabase or mafic dikes. So this is another important feature. So if you also remember back to the previous video, the presence of mafic rocks is often most associated with divergent plate boundaries. So the fact that we have these mafic dikes cutting through the area begins to suggest that yes, the area has obviously undergone some compressive tectonism at some point. However, it would seem that by the late Triassic and into the early Jurassic, the area was under extension. It was being stretched, and that would help to explain, should I say, the presence of these diabase dikes. Now, going back to these intrusions, these felsic intrusions, which are pretty much dominated by granite, or more accurately, metamorphosed granites. So these felsic intrusions display varying degrees of metamorphism, and where present, the metamorphic grade is lower than the surrounding Proterozoic and Cambrian aged rocks. So this is beginning to suggest that the emplacement of these felsic intrusions was part of the orogenic process. However, it was typically obviously a later stage portion of that process, because that would mean that these granites would have had less time to be affected by the metamorphic processes associated with the orogenic event. Now, when we look at our map of the Danville quadrangle, you can begin to see that there are several distinct regions. So if we begin by looking at the map, we can see straight away that there is clearly this region here, picked out by units which have a quite bright neon colour. They've got these dark blues, greens and yellows, so that area stands out quite a lot from the rest of the map. So that would suggest the presence of one domain there. You can also see that we have this area up here where we have this very large anticline or syncline. This region has clearly been deformed, and it's picked out in a range of yellows and green-yellow colours. So this would suggest that this region up here, once again, is another distinct domain within our map area. We also have this region over here in the east, that's picked out by a sequence of dark greens, dark pinks, and lighter pink coloured rocks. And so this area, once again, you can see it's obviously been quite strongly deformed, but the units within it are limited to this area. And so once again, that would suggest we have another domain in this area. Now, in the center of the map, you can see we have this region here, which is arguably the largest of the domains present on the map. And you can see it's dominated by this kind of creamy yellow colored rock. Then we have these pinks, we have these lighter greens, and we have these purples. And once again, the units within this region are limited to this region. So the boundary on the northern side is located somewhere along here, and the boundary on the southern side is located somewhere along here. And then finally, the remaining domain is located between this eastern domain here and this central domain here. And you can see it's actually quite linear, and it trends in an approximately northeast-southwest orientation. So if you come down to the diagram below, you can see that these domains have actually been marked out using these dashed red lines to denote the boundaries between them. I should point out that when we are doing this lab exercise, we're just going to be using these domains here. We are not going to focus on the Soratown Mountain Anticlinorium because it doesn't give us as much information as the other 4 domains. And so we're going to be focusing on each of these domains separately, and we're going to be analyzing them to get an idea of what has happened to this area during the Paleozoic and into the Mesozoic. Okay, so we're going to begin by looking at the Fries thrust sheet. I'm just going to zoom in over here on the right. Okay, so the Fries thrust sheet consists of a package of late Proterozoic and Cambrian age rocks, just like the rest of the map. And these have been deformed to produce large northeast-southwest trending anticlines and synclines. So when we look at the map area itself, we can see straight away we have the traces of these anticlines and synclines marked out by these dashed black lines. And you can actually see they're labeled. So this is the axis of an anticline, and then we have the axis of a syncline here. We have more anticlines and synclines to the northwest as well. And you can see these anticlines and synclines are all orientated approximately parallel to each other. And this would suggest that they have all been created by the same compressive event, because that convergent tectonism is going to produce multiple anticlines and synclines, and they're all going to be orientated approximately parallel with one another. Now, if we had anticlines and synclines in multiple different directions, that would suggest that there has been more than one orogenic event affecting this area. But the fact that we have just what appears to be one generation of anticlines and synclines within the Fries thrust sheet region would suggest that it's probably been affected by just one compressive orogenic event. Now, unlike the other Proterozoic and Cambrian age rocks within the Danville quadrangle map, the metamorphic grade for these rocks is noticeably lower, and it sits somewhere around green schist facies. That's going to put you in the low to moderate metamorphic grade range. And this is important because remember what we discussed earlier. Typically, when you have an orogenic event which produces a mountain range, metamorphic grades will be higher, in the core of that mountain range, and they will typically become lower as you move away from the mountain range. So the fact that we have these lower grades which are affecting these Precambrian and Cambrian rocks within the Fries thrust sheet gives us some idea of where this region of rock was located relative to the orogenic front and the resulting mountain range which was produced by it. Now, when we compare that to the rest of the rocks within the map area, they tend to show amphibolite to granulite facies metamorphism. So that's moderate to high grade metamorphism. That would suggest they are more proximal to the mountain range, the highlands. And so you can see straight away that based on the metamorphic grade alone, the Fries thrust sheet isn't actually fitting in with the rest of the map. Now, the other thing that you will probably have noticed is down here towards the southeastern corner, you will see there is a very heavy black line right there. That's a thrust fault. And this helps to explain why the Fry's thrust sheet is in this location. It's been thrust into the map area. So it's come from another location and it's been pushed into the map area due to thrust faulting. And the thrust sheet itself is free from Ordovician and Mississippian age intrusive rocks. So if you remember, other parts of the map area have been intruded by these Ordovician and Mississippian age rocks, but the Fry's thrust sheet has not. So we can work out straight away, number one, it's definitely been deformed at least once, and the metamorphic grades might suggest something about where it was located. Was it distal or proximal to the mountain range? And on top of that, we have an area of rock which is lacking intrusions which we find in other parts of the map. This, once again, gives us some idea about where this region of rock was located relative to the mountain range. Was it proximal? Was it distal? So think of a mountain range like the Andes and think of where the volcanic activity and intrusions which are associated with that kind of mountain range are found. Are they found within the mountain range itself, or is volcanism and intrusions found further away from the mountain range? Okay. So question 1 for the analysis of the Fry's thrust sheet asks us, based on the age of the rocks in the Fry's thrust sheet, when were they deformed? So were they deformed pre-Proterozoic, during the Cambrian, or post-Cambrian? So remember what we discussed in the previous video about the timing of deformation. Remember, you can only deform rocks which are already present. So look at the map area and look at the description. See which rocks have been deformed, and then once you know what the maximum age of the deformed rocks is, or should I say the youngest deformed rocks are, that will give you an idea of when the deformation occurred, because it must have occurred after the youngest deformed rocks. So question 2. Based on the orientation of the anticlines and synclines, what was the direction of stress that formed them? So if we look at our map here, we can see that this anticline is orientated approximately northeast southwest. And if you remember, when it comes to the formation of anticlines and synclines, the axis of them will be at 90 degrees to the direction of compression. So if our anticline is orientated northeast southwest, that means that the compressive stress must have been 90 degrees to that. Okay, question 3. What kind of stress produced the anticlines and synclines? So tension is the crust being stretched to form them. Shear is the blocks of crust moving past each other to form these anticlines and synclines, or were they formed due to compression, shortening? Question 4. So using the metamorphic grade and the intrusive rocks of the Fry's thrust sheet as a guide, how close was this region of rock to the associated highlands when it was being deformed? So think about the metamorphic grade and the lack of the intrusive igneous rocks, more accurately the lack of the intrusive felsic igneous rocks. And that's going to give you some idea about whether this area of rock was located close to or further away from the highland region. And obviously, please give an explanation as well as part of your answer for question 4. So now let's move on to the Smith River Allochthon region. So the Smith River Allochthon region consists of a block of rocks that have been transported into the area due to thrust faulting. And straight away, this sounds pretty reminiscent of the same process that brought in the rocks of the Fry's thrust sheet. So straight away, we can see a similarity of what's going on there. Now, this Allochthon region consists of a block of rock which is distinct from the rocks underlying them. And this is a strong indicator that the block formed in a different area and has then been thrust into its current location. So the Smith River Allochthon block consists of a sequence of late Proterozoic and Cambrian aged metamorphic rocks, which is just like the rest of the map area, and these rocks have been affected by moderate to high-grade metamorphism, producing gneisses, amphibolites, and schists. So right, straight away, we can see we definitely have an increase in the metamorphic grade. And this increase in metamorphic grade is associated with rocks which show foliation. So we have gneisses and we have schists that suggest compressive forces that are causing the minerals to align to produce the foliation. So the rocks within this region have been deformed to produce several antiforms and synforms. So this is probably a term you haven't heard before. So antiforms and synforms are like anticlines and synclines. However, they form in regions where the boundaries between lithologies are poorly defined. So when you actually look at the rocks, you can see that there is an anticline-like deformation to an area of rock, and you can see that there is a syncline-like deformation to an area of rock. However, you can't define the layers within it well, so that makes it very difficult to take structural measurements to actually definitively prove it's an anticline or a syncline. So instead what we do is we define them as antiforms and synforms. So an antiform is just like an anticline and a synform is just like a syncline. However, we can't define the layers of rock that make them up easily. Now, in terms of the orientation of these antiforms and synforms, they display a similar orientation to those which we observed in the Fry's thrust sheet, which would suggest that these antiforms and synforms and the anticlines and synclines we saw earlier are the result of the same compressive event. Now, the sequence has been intruded by two stages of Ordovician aged igneous rock. So we have an older, early Ordovician, intermediate to mafic igneous rock suite, and we have a younger, late Ordovician felsic rock suite. So straight away we can see that we have two completely distinct types of igneous rock present in our area. We have this intermediate to metamorphic group of rocks, intermediate to mafic group of igneous rocks, and this would suggest that they are probably related to some kind of divergent or extensional tectonism, because that tends to be associated with mafic igneous rocks. Now, then when we look at the late Ordovician rocks, we can see that we've moved to a felsic intrusion. And this is more suggestive of intrusions related to convergent tectonism. So we have granites and other associated rocks being produced due to subduction or crustal thickening, both of those resulting in the melting of the continental crust to produce these felsic magmas. So we can see that the Ordovician diorite and gabbro, so that's intermediate and mafic rocks, so these are the older Ordovician rocks, have been metamorphosed, while the granites display limited indications of lower grade metamorphism. So that also suggests that clearly something has happened during the Ordovician. So these earlier Ordovician rocks, so the older ones from the early Ordovician, they have been metamorphosed considerably more than the younger Ordovician intrusive igneous rocks. So this is telling us that clearly we have two different generations of intrusive rocks, and they have been affected differently by deformation or metamorphism associated with this convergent event. So this is giving us some subtle hints about the timing of the compressive event, the convergent event. So for question 5, what does the metamorphic grade of the early Ordovician rocks, so these are the older Ordovician intrusive rocks, the intermediate to mafic ones, tell us about the timing of their emplacement relative to the orogeny? So we have three options. They're intruded during the orogeny, they're intruded before the orogeny, they're intruded after the orogeny. So we know these rocks have been metamorphosed to moderate to high metamorphic grades, which would give us an indication about whether they were present before or after the orogenic event. Remember, metamorphism and deformation are connected together because they are part of the same event. So we know that for a rock to be deformed, it has to have been present before the deformation began. And so that should give you a hint about the answer to question 5. So for question 6, using the age of the intrusions as a guide, when did the orogeny which deformed the Smith River Alekthon occur? So remember, we have two different ages of intrusive igneous rocks, and they have both been metamorphosed. The older ones have been metamorphosed more, and the younger ones have been metamorphosed less, but they have both been metamorphosed. And we know this area has been deformed to produce the antiforms and synforms, and so it would suggest strongly that this metamorphism is connected to the convergent tectonism, to the orogenic event. And so in order to work out the timing of the orogenic event based on the intrusions, you need to find the youngest age, the youngest intrusion that has been metamorphosed due to the orogenic event. Because remember, just like deformation, metamorphism associated with the orogenic event can only affect rocks which were present before the orogeny began. So question 7, the anticlines and antiforms and synclines and synforms of the Frust-Frey sheet and the Smith River allochthon display the same orientation. What does this tell us about the orogeny that formed the anticlines, antiforms, synclines, synforms in the two regions? So they share a similar orientation, and that would suggest, I already touched on that when I was discussing the Frey's Frust sheet a little earlier, so I'm not going to go any further about that. So the next region as we move down is the Central Virginia Volcanic Plutonic Belt, and the name straight away suggests that you are clearly dealing with an area that contains both volcanic and intrusive igneous rocks. So this region does not display the presence of Precambrian age rocks that we see in other parts of the map. Instead, what we have is a sequence of Cambrian to Ordovician age sedimentary and volcanic rocks that have been metamorphosed, producing moderate to high-grade schists, along with some lesser gneisses, amphibolites, and marbles. Now, although metamorphosed, the metavolcanic units have been dated to the Middle Ordovician, so we know that's when they were being formed. We also have dating for Ordovician granites in the same area, and this puts their formation between 463 and 443 million years ago. So that's middle to late Ordovician. Remember, of course, the presence of these intrusive rocks is suggestive that there is an orogeny taking place during this time period. Now, unlike the Ordovician intrusive rocks of the Smith River allochthon, the granites of the Central Virginia Volcanic Plutonic Belt have been metamorphosed, producing gneisses. So these have been exposed to relatively high-grade metamorphism. So that's maybe giving you a bit of a hint about the proximity of this portion of the map when it comes to the relative location of the mountain range, the highlands associated with the orogeny. Now, the granites have been deformed along with the Cambrian and Ordovician country rocks, leading to them being folded into antiforms and synforms. So if we look over here on the right, it's quite a complicated map, but you can see that there are several features. So if we look right here, you can see this green unit. It clearly pinches off and closes up at this end, and it does the same thing here. And we can see the same feature picked out by this green dash line here, here, and here. So we can see we do have an area containing antiforms and synforms. However, compared to some of the other areas, it is a little bit more complex. It's a bit more messy, so they're not quite as easy to see. Now, the belt has also been intruded by Mississippian aged granites, which date to around 320 million years ago. Now, like the Ordovician granites, they too have been metamorphosed, producing gneisses, although they are of a lower metamorphic grade compared to the older granites. So these Ordovician age granites within this area have been metamorphosed to a higher metamorphic grade than the younger Mississippian aged granites. Okay, so question 8. Based on the ages of the granites present, how many orogenies has the Central Virginia Volcanic Belt experienced? And you're going to provide an additional piece of evidence to support the number of orogenies that you provide. So think about what's present in the area. we have these antiforms and synforms, and we have these intrusive igneous rocks. So think about which one of these two features is going to give us the best source of information about how many orogenies this particular area has been affected by. Question 9. So based on the ages of the Ordovician metavolcanics and granites, give a date for the start of the Ordovician orogeny. Remember, for something to have been either deformed or metamorphosed due to an orogeny, it must have been present before the orogeny began. So look at the three options you have here. Look at the ages of these Ordovician metavolcanics and granites and use that to tell you when the orogeny began. Okay, so the final part of the map we're going to look at is the Danville Basin. Now, the Danville Basin is actually this portion of the map right here. Okay, so we're going to ignore this portion to the north and northwest. We're not focusing on this. We're focusing on this region right here. And straight away, you will notice that there are several thick black lines, and this denotes the presence of faults. And you will actually notice that these faults occur along the northern side of the Danville Basin and along the southern side as well. So there's clearly some degree of fault control for this region of rocks. You will also see that you have the letters U and D on the maps for up prone and down prone. And we can see that the block of rock which represents the Danville Basin, which is this region coming up through here, is down prone, which would suggest that the fault we're looking at here is a normal fault. So straight away, that's a change from some of the other areas. We saw thrust faulting in the other areas. Now we're seeing normal faulting. Thrust faulting is typically associated with compression. Normal faulting is typically associated with extension. So when we look at the Danville Basin, we begin to see that it's not filled with Paleozoic aged rocks. Instead, it's filled with Mesozoic age rocks. So if we look over here on the blow up of the map, you can see that the letter codes for the rocks within the Danville Basin start with the letter T, which tells us straight away that these rocks date to the Triassic. So although we're clearly not looking at rocks which can be affected by Paleozoic processes, because that will happen in the past, we're going to quickly look at the Danville Basin because it gives us an idea of the evolution of the area post-Paleozoic. So, as previously mentioned, the Danville Basin is a linear body. It's approximately orientated northeast-southwest, and it's got faults either side of the basin itself. These faults are both normal faults, and the Danville Basin itself represents the down-prone block, so the block of rock that's dropped down relative to the other fault blocks. And so this means that the Danville Basin is classified as a graben. Now, the basin itself contains a sequence of red conglomerates, red sandstones, and red mudstones. If you remember, typically red-coloured sedimentary rocks are often associated with hot, arid conditions, so think deserts. So the sedimentary rocks themselves present a northwesterly dip direction and a dip of about 40 to 50 degrees. So they're dipping off towards the northwest. So that means they're dipping off towards the top left-hand side of the map, and they are dipping quite steeply at 40 to 50 degrees. Now, this dip is consistent along the length of the basin. So typically when we look at rocks that have been deformed, like the other rocks we've seen in the map area, you will tend to see the dip is somewhat variable. In this case, what we have is quite a consistent dip of between 40 and 50 degrees to the northwest. That would suggest that these rocks haven't been deformed, because then we would see quite a lot of variation in the dip. But instead what's happened is this block of rock has just dropped down as a whole block, a complete block. And as it's dropped down, it's rotated. And it's this rotation as this block of rock has dropped which has caused the dip in these layers of sedimentary rock. So that's telling us something about how the graben is behaving. It's causing this block of rock to drop down unevenly, and that's resulted in this dip that we can see here. So the igneous rocks within this basin are limited to late Triassic to early Jurassic diabase mafic dikes. So these are these mafic age rocks which instantly suggest that what we could be looking at is something which is extensional in nature. And that actually makes quite a lot of sense because we have these normal faults, which once again suggest the area is being, or the area is experiencing, should I say, some kind of extensional tectonic event. The area is being stretched. And so the presence of the Danville Basin is telling us clearly that after the compressive tectonics of the Paleozoic, something is happening in the Mesozoic that is beginning to put the area under extension. So, okay. So on to question 10. So was the Danville Basin formed due to compressive tectonics? Yes or no? And what's your evidence for that? And I think the explanation I just gave should hopefully give you the evidence for that answer. So on to question 11. What is melting to form the mafic magma that formed the diabase dikes? This is important. Please refer back to your notes. So we know that granite, so typically felsic and intermediate igneous rocks, are typically associated with the melting of continental crust. But mafic igneous rocks are not associated with the melting of continental crust. So look up and find what type of rock is typically melting to form mafic magmas. Question 12. Based on your answer to question 11, what type of plate boundary, excuse the spelling mistake there, had become active along the east coast of North America in the late Triassic to early Jurassic? So do we have transform tectonism, convergent tectonism, or divergent tectonism? And finally, question 13. What do the Triassic age sedimentary rocks of the Danville Basin tell geologists about the environmental conditions at the time? Once again, I touched on that when I was talking about the map area a few minutes ago. Okay, so this is going to be a good place to stop part 2. So please get up, have a walk around, get yourself a glass of water, and then please return for part 3.